Welcome back. In this lesson, we're going to explore a little bit more on theoretical probability, which is basically the idea of what's the probability something will occur if all outcomes are equally likely. And I will point out that we're going to do a couple of questions that we really can't make that assumption for, but we're going to anyway. And I'm going to try and really drive home when it's valid and when it's not necessarily valid, just so that you're kind of getting the difference. Okay, so our equation for theoretical probability is exactly the same as it was for experimental probability because it's just probability. And it's basically saying that the probability that event A occurs is equal to the number of ways that A can occur divided by the number of ways anything can occur. And if you think of it as sets, it's the probability of being within set A as the number of things in set A divided by the number of things in the universal set. So that's it. It's really just a straight up division. By the way, I do have several students that have asked me about how do I know when that P stands for probability and how do I know when it stands for permutation? And the answer is context. Um, if it was a permutation, then inside the bracket there should be a number, comma, a number, or at least a variable, comma, a variable. When it's just one thing like this, we usually it's obviously a probability and not a permutation. I will also point out that we can be as descriptive or non-descriptive as we choose to be when we put in what the A value is, the thing that's happening. Um, and we'll see that as we kind of go through. There's going to be a little bit of wishy-washiness when it comes to the notation that we use for the A and so on. Okay, so what is the probability that a student from the class chosen at random is wearing glasses? So I would write that as the probability of, I don't know, glasses. Now, I could have written a capital G and defined the set G as being all students wearing glasses, or I could just be a little bit more descriptive and put the word glasses in there. It really doesn't matter. As long as what you put in there is somewhat reasonable, I don't care. And the way that we would calculate this is I would count all of the students in the class that have glasses. So let's say that there are 7 students with glasses. And then I would count all of the possible students in the class. And let's say that there are 30 of us. Actually, I should say 30 of you. Since it's students in the class, I am not part of that universal set. Only students are part of that universal set. So then 7 divided by 30 works out to be 0.233 repeating. And I'm going to just remind you that despite the fact that the fraction and the decimal and the percent are all equivalent, and that as a percent would be 23.3%. The preferred method for this course of representing answers is as a percentage. So all 3 of those are valid, but I'm going to ask that you answer all questions as percentages. Assume that that's the format that is desired, unless I say otherwise, but it should be that one. Now, again, with significant digits and stuff, just be reasonable. I think here, if people rounded to 23%, I think that's reasonable, knowing that plus or minus a percent or half a percent is not a big deal when you're talking about 23. If the answer was 0.3, rounding it to 0 obviously is a little bit of a problem, and so on. Just be reasonable, usually 2 or 3 significant digits, and I'm pretty happy. I usually choose to do 3 or possibly more if the number's fairly large. Okay, if we have multiple events occurring, and this comes up a lot. So for instance, if we're flipping multiple coins, or if we're rolling multiple dice, or if we're drawing multiple cards from a deck, that one's going to be very special. We're going to talk about that one a little bit more later in lesson, I think, 4. But that one's kind of a special one. For now, let's think more about events like rolling 2 dice. As long as the outcomes of each of those have no bearing on the other experiments, that we can use this little equation, which basically is just another way of saying that the probability of A and B occurring is the probability of A times the probability of B. Okay. Now, if the 2 things are interrelated in some way, that is not necessarily true. Let's just take a look at an example. Number 1, find the probability of flipping exactly 2 heads when we flip a coin 3 times. Now, when I flip a coin, Flipping it a second time should not affect or be affected by what I got on my first flip. It's not like I flipped head, now I'm all out of heads on that coin. Um, each flip is independent of the others, and because of that, we can treat them as separate events, in which case our equation above holds. So what we want is the probability of two heads. And again, you can be as descriptive or non-descriptive inside that bracket as you'd like to be, as long as you tell me what it is you're finding the probability of. Okay, now this one I could try and do mathematically, but I think it's short enough that we can basically list all possible outcomes and just say what the probability is. So I'm either going to get all heads, head, 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 or I'm going to get two heads and a tail. If I get two heads and a tail, the tail could be in the first, second, or third spot. So tail, head, 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 tail, head, 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 tail. Okay, so that was three heads, two heads. I could also get one head, and I can get it in three ways. It could be in the first, second, third spot. So head, tail, 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 head, tail, 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 head. And my last possible outcome would be that I get all three tails. Okay, so now we have 8 possible outcomes. So that means that the bottom is going to be an 8. And we want the ones that have heads exactly twice, or exactly two heads. And that happens here, here, and here. So that's 3 out of 8. And 3 out of 8, I believe, is 37.5%. Once we've done the division, 3 divided by 8, and then converted to a percent by multiplying by 100%. Now, is there another way of doing that? The answer is yes, there is. I'm not going to focus too much on it today because we're going to be looking at it a little bit more as time goes on. But another way we could have mathematically done that one, if we didn't want to list all the possible outcomes, is to say on the top, the number of ways of getting 2 out of 3 heads would be 3 coins choose 2 heads, which happens to be 3. And on the bottom, the number of possible outcomes, since each coin has 2 possible outcomes, there's 2 outcomes and 2 outcomes and 2 outcomes. That's 2 times 2 times 2. And 2 times, 2 to the exponent 3 is 8. So there's where we got our 3 and our 8 from if we wanted to do it mathematically. I think you could extend this now and say if we were flipping 21 coins, what's the probability of getting exactly 7 heads? It would just be 21 choose 7 over 2 to the exponent 21. So the second method that we just looked at there is much better if you're trying to do bigger values. But again, we're going to kind of ease our way towards that idea as we go through these. Question 2. Find the probability of rolling a sum of 7 or 11 when rolling a pair of die. Now, there's different ways we could tackle this one. The way that I'm going to use, and I would recommend that you use it too, is by making something called a dice table. It seems like it's something that takes forever, but it actually is relatively quick. So just as an example here, you can kind of see how long this will take me. What I'm going to do is make a 6x6 table. It's probably take me longer actually than doing it on paper just because it's a little bit harder to draw on the tablet. And then what I'm going to do is I'm going to say my first roll can be a 1, 2, 3, 4, 5, or 6. And my second roll can be a 1, 2, 3, 4, 5, or 6. And since I'm looking for a sum of 11 or 7 or 11, I'm going to just put the sum of each 2-number combination in here. So if I rolled 2 ones, that's a total of 2. If I rolled a 1 and a 2, I get 3, or a 2 and a 1, I get 3. And what I think you're going to see if you fill in this table relatively quickly is that the diagonals are going to be the same. Or you can say that as you basically start each row 2, 3, 4, 5, 6, 7, and then just increase by 1 each time as you go down. Whichever way you want to think about it, you can make this table pretty quick. At least quickly enough that it's worth it if you're going to get the answer right. So that didn't take too long, maybe 30 seconds or something like that. And what we want is the probability of getting a 7 or an 11. So what I'm going to do is look on the table and say, where are the 7s and the 11s? And oops, the 7s are along the diagonal. The 11s are down there. So there's 1, 2, 3, 4, 5, 6, 7, 8 ways that I can get what I'm looking for. So I'm going to do probability of 7 or 11. Again, just being descriptive inside that. We'll worry about a little better notation in Unit 5. But for now, just be descriptive. Probability of getting a 7 or 11. There were 6, 7, 8 ways of getting it out of 36 possible things that we could get. Now, I do want to point out that I have had a lot of students in the past that'll say, well, there's only 11 possible outcomes. You roll a 2, a 3, a 4, a 5, a 6, a 7, 8, 9, 10, 11, or 12. And you there's 2 ways you can get what you want, a 7 or 11. So it's 2 out of 11. That doesn't exactly work because every different way of getting a 7 or an 11 or any other number does count as a possible outcome, even though the number of unique outcomes is actually only 11. The number of possible outcomes in this case is 36. So then we just say 8 out of 36 in lowest terms would be 2 over 9 or 22.2%. Okay, so hopefully you're not finding this too painful. Again, it's just what are the possible ways things can occur and what are the number of ways that you get what you're looking for. All right, question 3. There are 9 horses entered in a race. Each horse wears a different colored coat in the race that can easily tell them apart. What is the probability that the red horse will come in first, the blue horse will come in second, and the green horse will come in third? Now, before we even begin this, I want to point out that this very much seems like an experimental probability problem because we already talked about how some horses may be faster than other horses, and we have absolutely no way of taking that into account with theoretical probability. What makes this question actually theoretical is that the colors, as far as we know, are randomly assigned to the horses. So even though some of the horses may be faster, that doesn't mean that the red jacket or the red coat that's put on a horse has any different chance of winning than the blue jacket because we don't know what horse they're going on. So if we focus on basically the jackets or the coats instead of the horses themselves, then this is a theoretical probability problem where every color has an equal opportunity to come in any given spot. Okay, so how do we approach this? I'm going to start now by just telling you that there are actually several ways to approach this one, and all of them should yield the same answer, assuming that we do it correctly. So I'm going to start off with the probability of, we want the red to come in first, then blue, then green. So I'm just going to do red, blue, green. Again, just a descriptive notation to remind myself what it is I'm finding the probability of. And now let's think about the different ways that we could possibly approach this problem. I think the easiest way to do it is to ignore all the horses that come in 4th through 9th because they don't actually have any effect on the problem. Doesn't matter where the white horse or the purple horse or the blue, it doesn't matter where the blue one is. The yellow horse, doesn't matter where those are, as long as the first 3 are red, blue, green. So if we're only looking at the first 3 horses, there's only one way that they can come in that order, red, blue, green. It has to be red, then blue, then green. And the number of ways that the first 3 horses could be chosen would be 9 times 8 times 7. There's 9 ways that the first horse could be chosen. It could be any of 9 colors, and then the second horse would be any of the 8 remaining colors, and the third horse would be any of the remaining 7 colors. I think I said that correctly. Anyway, when we work that out, 9 times 8 times 7, 9 times 8 times 7, get my calculator to work properly, is 504. So this is 1 out of 504, which I can then write as a percentage. So I'm going to point out that when I do 1 divided by 504, I get 0.00198. To convert that into a percent, I multiply by 100 and get 0.198%. So roughly 0.2% or 1 in 500 chance. And that's pretty close to 1 in 500, 1 in 504. Now, another way I could have thought about this problem is to actually consider all of the horses and say, okay, how many ways can the horses come in? So the first horse has to be red. There's only one way that can happen. Second horse has to be blue. Third horse has to be green. And then of the 6 remaining horses, the fourth spot could go to any 6 of them. And then 5, 4, 3, 2, and 1. And on the bottom, the 9 horses can come in 9 factorial different orders. And when you do that, you realize that you have 6 factorial on the top divided by, the top part there, if we evaluate it, is 720. The bottom part, 9 factorial, is 362,880. And when I simplify that, yeah, it's exactly the same thing as it was before, 0.198%. Okay, I realize I'm running out of room a little bit, but there is actually another way I can think about this one. So let's approach it this way. Now, ultimately, this math is going to look exactly the same way as the first one, but it's a different way of thinking about it. Instead of thinking of overall the horses coming in one way, and then on the bottom there being 504 ways the first 3 horses can come in, I could think of these as 3 events. I could think of what is the probability that the first horse is red, and that would be 1 in 9. And then I ask myself, what is the probability that the second horse is blue? And that should be a 1 in 8. And what's the probability that the third horse is green? The probability of that happening is 1 in 7, since there are 7 horses left. And I think mathematically, you could look back at the first way we did it and see that 1 over 9 times 8 times 7 is exactly the same thing. So mathematically, this is the same way as the first version we looked at. What differs is whether or not we think of this as one big event, 3 horses coming in that order, or whether we think of them as 3 independent events, the red coming in first and the blue coming in second and the green coming in third. Now, obviously they yield the same thing, so it doesn't matter, but again, it has to do with the thought process and how your brain attacks the problem. And sometimes you'll see one of these obviously, and you may not even see the other one. The good news is if you can see any of the methods, you should get the right answer. I just want to show you that different logics do get the same answers if they're all correct logics. Question 4. A committee of 5 people must be selected from a group of 10 males and 8 females. What is the probability that there are exactly 3 males on the committee? So now I want to point out that we actually did questions just like this back in our last unit. The only difference is I would have said in how many ways could you get exactly 3 males on the committee. Now I'm saying what is the probability that there will be 3 on the committee. So we could say the probability of 3 males. Now if we think about how we would have approached this when we did it in the last unit, the number of ways of getting 3 males would be to say we have 10 males, I need to choose 3 of them. And the other part would be we have 8 females, we have to choose 2 of them. So that's our number of ways of picking 3 males. Now the number of ways of picking any 5 people would just be 18 choose 5. So basically, this is the question we could have done last unit. At least we could have done the top and the bottom separately to each other. Now that it's a probability problem, we just have to work out what the top is and what the bottom is and then divide. Okay, so punching this into my calculator, 10 choose 3 times 8 choose 2 is 3,360. And on the bottom, 18 choose 5 is 8,568. And when I do the division, I get 0.392 or 39.2%. That's a relatively high percentage, but at the same time, if we think about it, there's slightly more males than females. So if we choose 5, it makes sense that it's going to be significantly likely that our group will have slightly more males than females. So it really is just a ratio issue. We're picking a very similar ratio in our sample to the one that we are picking or had in the original group. So we get a fairly high percentage or a fairly high probability of that happening. All right, one more to finish off the day. Two-parter, but that's okay. In a raffle, there are 25 tickets sold. You bought 4 of them. There are 3 prizes being given away. What is the probability that you will win exactly all 3 of the prizes or exactly one of the prizes? All right, so let's think about this. Now, as with most of these types of questions, the easiest way I think you can approach it is to picture yourself actually doing this. Picture yourself sitting in the audience where they're drawing the prizes. You're holding 4 tickets in your hand, and you know that there are 25 possible tickets that can be drawn from. So if you keep that in mind, I think this question's not actually too hard. So we'll do the probability of 3 prizes. Again, just description in the brackets. So here's how I want you to think about it. The first prize is about to be drawn. What is your probability of winning it? Well, you have 4 of the tickets. There are 25 tickets out there. That means you have a 4 in 25 chance of winning. Okay, so that's the probability that you won the first prize. So you walk up to the stage, you hand them your winning ticket, they check it, they throw it in the garbage along with the ticket that was drawn, which matches yours. And now they are about to choose the second prize. For the second prize, what's your probability of winning it as well? Well, think about it. You're holding 3 tickets. There are 24 tickets left for them to draw from. The probability of you winning is 3 in 24. You go up to the stage, claim your prize, they throw out the tickets, you sit back down. Probability you win the last prize, you have 2 tickets remaining. There are 23 to be drawn from. Your probability of winning is 2 in 23. Okay, now I'm going to point out that we could have done a similar logic, and mathematically it's identical. I'm going to do one extra step here before I write down the answer and point out that the top is really just 4 pick 3, and the bottom is really 25 pick 3. So if you win all 3 prizes, the number of ways you could do that is to pick which of the 3 tickets you're going to win with from your 4. And the number of ways that that can happen is that they can have 25 numbers and they pick 3 of them. And regardless of which logic you use, 4 pick 3 divided by, actually I'm going to write out one more step here, I suppose. The top number, regardless of whether you use the permutations or the original just multiplications, is 24. And the bottom is 25 pick 3, which is 13,800. And 24 out of 13,800 is 0.00174. Multiply that by 100%, and you get 0.174%. Now that's pretty low, but I mean, think about it. Your probability of winning all 3 of the prizes should be fairly low, even if you had 4 of the tickets. I also want to point out that this one, by a little bit of coincidence, the 24 on the top could be canceled with the 24 on the bottom of our original 3 numbers. And so the bottom, it's really just 1 out of 25 times 23. And if you do that, it's 1 in 575. Either way. And that's something that can happen. It won't always happen, but often you get a little bit of cancellation because of the way these numbers tend to work. Okay, a slightly harder problem. And by slightly, it's actually relatively harder. We want to win exactly one of the prizes. Okay, so there's basically 3 different cases or 3 scenarios that this can happen as, and that's basically you win just the first prize, or you win just the second prize, or you win just the third prize. So we win first or second or third. We can't win more than that. Now, if we win the first prize, we're going to approach this just like we did part A. Our first prize, we have a 4 in 25 chance of winning. However, we now have to lose the second prize and the third prize. So our second prize, last time we said there was a 3 in 24 chance of winning, which means that there is a 21 in 24 chance of losing, which makes sense. There are 21 tickets that are left out there to be drawn from, and 21 tickets that will cause you to lose, and 24 tickets that will be drawn from. Once that one has been drawn and someone else goes in up and claims the prize, then your next one, there are 23 tickets left. You still have 3 tickets in your hand, which means there are 20 ways to lose. Okay, now we do the winning this just the second prize. Because it's an or, we do addition. When it's ands, we do multiplications. When it's ors, we do additions. So now we lose the first prize. Well, losing the first prize means it could be any of the 21 out of 25 tickets. Can't be the 4 that you have. And you're going to win the second prize. There are 24 tickets left, and there are 4 winners. 4 in your hand, so 4 out of 24 chance that will happen. And then the third one we're going to lose. There are 23 tickets left. You were holding 4 tickets. You've won once. You have 3 tickets left, so there is a 3 in 23 chance you'll win, which means a 20 in 23 chance you will lose. And finally, we're going to lose the first one. I'm going to kind of just skip through this a little faster. You're going to lose the first one. There are 25 tickets for that, 24 for the second prize, 23 for the third. Your first one, none of your 4 tickets can win, so that means there's a 21 chance, or 21 ways you can lose. The second one, there are 24. You have 4 tickets. There's 20 ways you could lose. And the last one, there are 23 tickets. 4 of them are yours, and you need to win, so it's a 4 in 23 chance you'll win. Now, before I start pulling up my calculator and doing all of this, what I want you to do is realize that all 3 of these scenarios turn out to be identical. Where the numbers are changes, but the actual numbers themselves don't. In all 3 scenarios, you have 25 times 24 times 23 on the bottom. And on the top, despite the fact that the order changes, you do have a 4, a 21, and a 20 in each of these problems. And since there are 3 of those, I'm just going to multiply that by 3. Now you could skip this step if you wanted to and just evaluate the top step. Same answer, just takes you a little bit longer. Okay, once you've done that, I'm going to try and do this all in my calculator at once. I think I can. By the way, if you get a different answer than me, it's probably because you're not using BEDMAS properly. Remember that 25 times 24 times 23 on the bottom need to be evaluated before you do the division. So the way I do that in my calculator is I'm going to do the top part. So 3 times 4 times 21 times 20. And then I'm going to do divide by 25 equals divide by 24 equals divide by 23 equals, and I get 0.274 or 27.4%. 27.39 something to be more precise, but we'll round off to 27.4. If you get a number greater than 100 or just way too big, it probably means that you're putting into your calculator 3 times 4 times 21 times 20 divided by 25 times 24 times 23, and your computer or your calculator assumes that you want the 24 and 23 on the top. It's a very common mistake that I see, so I thought I would point it out. Okay, so hopefully you're starting to get a hold of the kinds of logic that we use here. And I want you to understand that it seems like there's a million things that we can do here, or a million ways we can approach the problems. They all come down to that one basic equation of the probability of something happening equals the number of ways it can happen over the number of ways anything can happen. The details are basically our previous units. So it's not that we're approaching these things in a million different ways, it's that we have to use all of the stuff that we've learned in the permutations and combinations units to figure out what that top and bottom number are. And the only way you're going to get better than that is practice. So go do that now, and let me know if I can help you in your struggles. And there probably will be some struggles. Anyway, till next lesson. See you later.